Hi there. Welcome to the second part of our lecture on the functional units of the nervous system. And I really think this is, we need a better name for this lecture because, we've already really talked about what neurons are and the different parts of neurons and how we identify them. What this part of the lecture is really about is not talking about so much how neurons look, but about what they do. In particular, what we're doing in this lecture is we're getting ready to talk about the resting potential and the action potential, which are two of the most important concepts in cellular neuroscience. So really where we're headed here is we're headed to this description of how neurons maintain an uneven distribution of charges on either side of their membrane. This is called the resting potential. And then how they have these waves of electrical activity that travel down the axon. This is called the action potential. But to really fully understand what's going on here, we need a little bit of preparation, and that's what we're doing today. For this, I would actually recommend that you go ahead and read section 4.1 of chapter 4. We'll get into more of chapter 4 in the next week's lecture, but if you want to be sort of read up on the material that we're covering today, read section 4.1. So what are we going to do today? We are going to review basic electrical terminology. We're going to talk briefly about the sort of tools that are used to measure electrical activity in neurons. We're going to go over some key concepts, and these are probably the most important preparatory concepts that we need. And finally, we're going to try to pull these concepts together and discuss and do a quick preview of the resting potential itself. And again, we're going to go over some of these things in our next week's unit when we talk in detail about resting potential and action potential. But what I really want to do here is just sort of lay the groundwork for that. All right, so let's start with a few electrical concepts and terminology. Depending on your background, if you've had some fairly robust physics courses, this should all be elementary to you, should all be a review. But just in case it isn't, I wanted to go over it now. So first of all, we need to talk about the concept of charge and ions. Remember, charge is just a fundamental property of matter. Protons have a positive charge and electrons have a negative charge. And the net charge on any given atom is going to be determined by the balance between protons and electrons. Atoms that have a net positive charge because they have too few electrons, or atoms that have a net negative charge because they have too many electrons, are called ions. We already talked about two important ions, the chloride ion with a net charge of -1, the sodium ion with a net charge of +1. In addition to that, for neural transmission, we're also going to be talking about calcium, which has a net charge of +2, and potassium, which also has a net charge of +1. Now, the most important thing we need to know about charges and ions is how they behave towards one another. Things that have opposite charges are attractive to one another. So two atoms with one with a net positive charge, one with a net negative charge, if they can, will be drawn closer together. Whereas like charges repel. So any two atoms that have the same charge will be repelled from one another. Now this process of attraction and repulsion is something that we can actually measure. And we can measure that by something that is a term that's familiar to you, which is called voltage. Really, voltage is, when we're measuring voltage, what we're measuring is the force that is acting on charges that may be attracted to one another. Another way of putting this is that if you separate positive and negative charges, there's going to be some force, some electrostatic force that is going to be driving those charges towards one another, and that force is the voltage. So for example, so one important thing we need to know about voltage is that voltage is always measured between 2 points. So for example, if we think of the terminals of this battery here, and if we hooked up a device to measure voltage and we attached one end of that device here and the other end of that device there, it would tell us that it has a voltage of 9 volts. And what it's telling us there is it's measuring the amount of force that is drawing the charges between these two terminals towards one another. When we do the same thing for neurons, when we measure the difference in voltage between the interior and the exterior of a neuron, we see that it reads at negative 70 millivolts approximately. So what that's telling us is that neurons at rest maintain a net negative charge in their interior relative to their exterior. Now, what happens when we take the, let's say we take a wire and we connect these two parts of our battery, these two parts for which we've already measured, and we already know that there's a separation of charges, and there are charges that are being attracted to one another and trying to get towards one another. We get current. Current is simply the flow of charges that is driven by a voltage, that is driven by a separation of charges, that is governed by these forces of electrostatic attraction. Current has to flow through some medium, and in general, a conductor is a medium, is a substance that easily allows charges to flow. An insulator, on the other hand, is a substance that does not allow charges to flow. So if you imagine if we broke this circuit and put an air gap here, the flow of current would stop, because current does not flow very easily, as easily through air as it would through a metal wire. Now, what does this have to do with neurons? Remember that neurons have a cell membrane. The cell membrane divides the intracellular and extracellular portions of the neuron, and it's composed of this bilayer of phospholipid molecules. Now, the extracellular fluid of a cell, right, is this salty aqueous environment. It is generally a conductor. It is very easy for charged particles, for current, to flow through the extracellular fluid. The same thing is true of the intracellular fluid. The intracellular fluid, again, it's this salty aqueous environment. It's very easy for charge to flow within the intracellular fluid. The membrane, however, this phospholipid bilayer, these fatty acid tails, are essentially a form of insulator, which means that it's going to be very difficult for charge to flow through the phospholipid bilayer. And now this is the property of the membrane that allows it to maintain this net negative charge on the inside and net positive charge on the outside. Now, as we'll see later, and as I've mentioned before, the neuron's membrane is not just the phospholipid bilayer. It contains channels and other things that do allow ions to pass through. But we'll get to that detail later. The important thing to keep in mind is that, at least when we're talking about the phospholipid bilayer itself, that is an insulator, and that is what allows the neuron to maintain this separation of charges, to maintain this net negative voltage on the inside. All right, now, you might ask yourself, how on earth could we measure this voltage, this difference in electrical potential? And I just want to briefly talk about the sort of tools that neuroscientists use. In general, the tools that we use are a microelectrode that is coupled to some sort of voltage measuring device. And what we want to do with this microelectrode is we want to take one electrode, and we want to use that electrode to gain access to the interior portion of the cell. Right, so that's the one point that we're looking at. And then for the other contact, for the other sort of half of our voltage measuring device, we want to place that somewhere that is continuous with the extracellular fluid. So if we sort of zoom in here to the tip of this electrode, we can see that it can come in a few different forms. It can either be a thin tube of glass with an open tip, right? So we have this saltwater solution which becomes continuous with the interior of the cell once the interior of the cell is punctured. Generally, these usually then have some sort of metal wire inserted within the conductive solution that then goes into the voltage measuring device. You can also use just a straight up metal wire that has insulation all around it, with the exception of the uninsulated portion of the tip that is inserted, again, inside to the cell, that is made continuous with this interior portion of the cell, so that essentially one part of the device is inside the cell, the other part of the device is outside of the cell, and the voltage measuring device then can sense the difference in electrical potential, can sense the separation of charges, and measure the voltage. Now, the voltage measuring device here, I'm being sort of generic about it, There are several different devices you can use. The most common one is called a oscilloscope, and oscilloscopes, in the old days were made of, vacuum tubes and cathode ray tubes. Now they're all digital and they're all hooked up to computers, but they all function in the same general way. What oscilloscopes do is they measure voltage over time. So let's imagine in our minds a little experiment we do where we take our oscilloscope here and we have one end that's hooked up to the extracellular space and we have another end that's hooked up to this electrode. And at the beginning, let's imagine that that electrode is outside of the cell. So if it's outside of the cell, that means that this electrode and this wire here are all continuous with the extracellular space. And because the extracellular space is a conductor, and because charge flows easily within a conductor, we know that there's not going to be any net difference in charge between this part of the extracellular space and this part of the extracellular space here. They're all going to be at the same net charge, which means they're going to have no separation of charges, no voltage difference between them, and we're initially, before the electrode goes in, going to measure a voltage of 0. Then, if we were to take that electrode and just advance it quickly so that the tip drops inside the cell and gains access to that intracellular space, then we would see the voltage drop immediately down to a level of about -70. Now, if this is a neuron, let's say, that's still alive and that's still healthy, once the electrode is inside, if you wait patiently enough, or maybe if you stimulate the cell, you'll see this. You'll see the voltage briefly leap up and go anywhere, can reach 0 or even go above 0 to a positive voltage level, meaning that there's momentarily a net excess of positive charge inside the cell. And then you'll see it very quickly drop back again to this lower level. This low resting level here, this sort of approximate -70 level, is called the resting potential. And this brief leap and drop that we see is called the action potential. Now again, we're not going to talk about the details of what drives the resting potential and action potential. We're going to save that for the next lecture. But these are sort of the two kind of fundamental phenomenon of what neurons do, is they maintain this net negative charge at rest, but then it's interrupted by these dramatic increases in charge, these dramatic increases in voltage that then quickly drop back down to rest. Okay, now we're getting into what I think are some of the most important concepts, and hopefully these aren't totally new to you. We're going to talk about the idea of gradients, diffusion, and permeability. Alright, so what is a gradient? A gradient, very simply, is what happens anytime you have an unequal concentration of something between any two different places. So for example, if this sort of little toy example here, if you take some ink and you drop it into a beaker full of water, at the instant it drops in, there's going to be an unequal distribution of ink on one side of the container relative to the other. There's going to be a gradient of this substance. Now, over time, that substance is going to spread out, and over a long enough period of time, it's going to reach a continuous distribution all throughout the container, and the gradient is going to disappear. So this process of spreading out and filling the space is called diffusion. It's simply the movement of some substance from an area of higher concentration to an area of lower concentration. For neurons, there are two kinds of gradients that we're interested in. There are electrical gradients, which is an unequal distribution of charges. We could also call that a separation of charges, or a voltage if we like. And a chemical gradient. A chemical gradient can also be called a concentration gradient, and that simply means an unequal distribution of some particular molecule. Now, again, this is another sort of toy example. If we imagine, instead of pouring this ink solution into our beaker, we pour in a solution of salt water, a solution that's filled with charged particles. We start off, first off, with a concentration gradient, because there's this chemical substance here that is unequally distributed throughout this jar of water. Also, in some sense, we do have a voltage gradient, or at the very least, we have an unequal distribution of these charged molecules as well. So what's going to happen over time is these molecules are going to diffuse, and they're going to diffuse, first of all, according to their chemical gradient, so that there's an equal distribution of these substances throughout the container, and they're also going to diffuse according to their electrical gradients, or you can think of it as their electrostatic gradients. They're going to diffuse such that there is an overall net equal distribution of charge throughout the entire container. Okay, so let's now make our example a little bit more complicated. And let's go back to our friend here, the phospholipid bilayer. And remember that the lipid portion of this makes our membrane an insulator, and it's capable of maintaining a separation of charges. And what that means is, in general, ionic substances, charged particles, are not going to be able to cross through the phospholipid bilayer. So if, for example, we took a container again and we filled it with salt water, but instead this container is divided by a cell membrane. If we do that, the salt solution will eventually diffuse to fill one half of the container, but it won't be able to diffuse to the other half because the cell membrane is going to prevent the movement of any of these charged particles. All right? So that's hopefully should be fairly intuitive, right? It's the same thing that we saw here. We're getting diffusion, again, to sort of, the substances are diffusing down their chemical and their electrical gradients to meet an even distribution. And the same thing is happening here, except, of course, it's only happening in one half of the container because you have a cell membrane separating it from the other half. All right. Now remember, though, and I've mentioned this several times, the membranes of real living cells aren't just made of this phospholipid bilayer. They contain channels. They contain channels that selectively pass certain ions to the exclusion of others. So I've used this word before. This makes the membrane not impermeable, it makes it semi-permeable. Or another way to put this is that it is selectively permeable. And this concept, this property of selective permeability of the membrane, this is the key mechanism that makes the resting potential and the action potential possible. So if you can understand what this selective permeability means, and if you can think sort of in a mechanistic way about what happens to ions through selectively permeable membranes, you're going to be able to understand the resting potential and the action potential. And I think the book actually has a very nice toy example that illustrates this. And I'm going to sort of walk us through it now. So let's go back to our jar filled with a salty solution, and let's imagine now that instead of having just a plain old phospholipid bilayer separating the two halves of our container, instead we have a membrane that contains channels that permit the flow of chloride ions. So this is a semi-permeable membrane, a selectively permeable membrane for chloride ions. Okay. So now, what happens to the molecules here, to the atoms here? Well, first off, let's think. What are the gradients that exist between the two halves, these 2 points in space here, these two halves of the container? What are the gradients that exist? And this I should say is where I'm going to have you sort of quiz yourselves and let yourselves think critically about this. What gradient do we see that exists here? Well, very clearly, we have a chemical gradient. We have an unequal distribution of these chemicals. In this case, the positives are sodiums and the negatives are chlorides. We have an unequal distribution of them between these two halves of the container. So what's going to happen? What do these molecules want to do? They're going to want to diffuse. So what then is going to happen? What's going to happen to the chloride ions, and what's going to happen to the sodium ions? And let's imagine that we've allowed time to pass. So what has happened to them? Where are the chloride ions? Where are the sodium ions? Well, remember that the sodium ions, they can't go anywhere. This membrane is only permeable to chloride. So we imagine that what's going to happen is that we're going to have some chloride ions that are going to diffuse down their chemical gradient from this half of the container to the other half of the container. All right. And let's imagine we've let that happen for a little while. So let's think at this moment in time that I'm circling here with my mouse, what are the gradients that exist now? Certainly, we still have this chemical gradient with sodium, and that's not going to change. But what about the chemical gradient with chloride? Well, we've allowed chloride to flow down its chemical gradient, so at some point, we are going to hope that that chemical gradient between the two halves for chloride is going to decrease a bit. But now, look at what we have on this side of the container. On this side of the container, we only have chloride ions, negatively charged chloride ions. Here, we have a mix of the sodium ions and the chloride ions, but we have more sodium than chloride. So what does that mean? What do we have between these two halves of the container? What we have is a net negative excess of charges here and an excess of positive charges here. We have a separation of charges. We have an electrical gradient in addition to these chemical gradients. And what's important, and this is probably the most important critical point, at the beginning here, the chemical gradients are pushing our chloride ions from the left side to the right, to the area of higher chloride concentration to lower chloride concentration. Now what we have over here is, in addition to that, we have an electrical gradient. We have a net negative charge over here and a net positive charge over here. Chloride ions are the only charged ions that can move between them. Because we have this separation of charges, chloride ions are going to be attracted. Remember, opposite charges attract one another. Chloride ions are going to be attracted back over to the left side of the container, while at the same time, the chemical gradient is going to be pushing chloride ions over to the right. And what's going to happen over time is that the distribution of chloride ions between the left and the right half of the container is going to reach what's called equilibrium. Equilibrium meaning that the force of the chemical gradient that's forcing the chloride from the left side to the right is going to just about equal out to the force of the electrical gradient that is going to tend to force chloride from the right to the left. And what's going to happen is you're going to have chloride ions crossing from left to right and right to left in equal numbers, and therefore reaching a sort of net stable level of concentration between them, and also reaching a net stable charge. So what you're going to find is if you took, let's say, an oscilloscope and put one end of it here and one end of it there, what you would find is that the voltage would eventually settle out over time to represent a net negative charge in this side of the jar. Now, I've explained that all here, sort of in this slide. So if you don't want to sit and listen to that entire description, you can read through this slide. I also recommend just reading the book because I think the book describes this very, very well. All right, so this idea here, this idea of diffusion of charged particles through a semi-permeable membrane to the point that balances the chemical and electrical gradients and therefore reaches equilibrium, this is sort of the key idea of what drives the resting potential. In this example here, right, we had this sort of imaginary setup where we've got a container with two sides and we've put salt inside that container. If you can understand what's happening here, then you can understand what's happening in a neuron because it's more or less the same thing. In the case of the resting potential, it's not chloride that's the main driver, it's potassium that's the main driver. But you'll see, if you can understand the example that we just went through, you're most of the way to understanding how the resting potential works. All right, with that, we're going to wrap up. I just want to cover, again, summarize what we did and talk about our learning objectives. At the end of this, you should be able to define these basic electrical concepts: current, charge, voltage, and so forth, and you should be able to understand them. You should be able to understand what they mean, especially in terms of neurons and the kinds of charged particles and ions that exist in neurons. You should understand how electrodes and oscilloscopes are used to measure the voltage inside of neurons. And finally, and this is the most important thing, is you want to be able to understand the difference between chemical and electrical gradients. You want to understand what those are. You want to understand how these gradients drive diffusion through a semi-permeable membrane, and understand the idea of equilibrium between these gradients. So once you have these, and once you feel like you've got those firmly in your mind, you're going to be able to get the resting potential and later the action potential. All right. So that is the end of this week's lectures. I'll of course see you in the Q&A if you have any questions. And until then, be well. Thank you very much.